The best image was taken on October 2nd by the HiRISE camera on board the Mars Reconnaissance Orbiter. And unfortunately, the argument is because of the government shutdown, this data was never released.
In recent weeks, a researcher known as Avi Loeb has shared a series of observations and comments that noticeably shift the direction of the discussion surrounding the object Atlas. The key updates are the first radio detection made by the MeerKAT radio telescope, and a new set of optical images showing a complex network of jets emerging after perihelion. Both findings appeared as the scientific community continues to demand high-resolution data, some of which, according to Lowe, still remain unreleased. The major development is the registration of a radio signal detected by South Africa's MeerKAT telescope. Observations revealed absorption lines associated with hydroxal O molecules, a chemical marker typically linked to ice breakdown or surface sublimation. According to Avi Loeb, this indicates that Atlas is thermally active, releasing material as it interacts with radiation from our sun. It's important to highlight the technical aspects. The detected lines appear in absorption, not emission, meaning that cooler gas lies between the object and a warmer background radiation source. The width of the signal matches what would be expected for an object at the temperature corresponding to its distance from the sun at the time of observation. The velocity analysis also matches perfectly with the object's relative speed and the telescope's observation angle. The Doppler shift fits the calculated parameters. The optical frames taken on November 8, 2025 were composed of 24 green filter exposures, 35 seconds each, with several additional red and blue frames. The result reveals a bright, persistent halo, roughly 500,000 kilometers across, and at least 7 distinct jets, several of which are directed sunward. Observers cited by Lowe note that these frames were captured under challenging conditions, bright, moonlight and twilight, making the persistence of these structures all the more convincing. Lowe emphasizes that neither explanation should be ruled out prematurely. Both require careful testing. Natural interpretation. The jets could originate from localized ice patches on a comet-like nucleus, releasing gas and dust when heated. This can produce anti-tails and jets oriented in multiple directions. Got technological interpretation. The jets could correspond to attitude control or propulsion thrusters, controlled jetting consistent with the operation of a spacecraft. Lowe draws no final conclusion, insisting instead that the technological hypothesis must remain on the table until higher quality data becomes available. One of the most intriguing observations is the mismatch between the measured, non-gravitational acceleration of Atlas and the absence of any visible debris cloud. Interferometric data show a trajectory deviation requiring additional non-gravitational terms in orbital models. If this acceleration were caused solely by outgassing, the conservation of momentum would demand an enormous mass loss, around 1/16 of the object's total mass, roughly 15%, or about 5 billion tons. Such ejection should have produced a bright, easily observable cloud, visible to many observatories worldwide. Yet no such massive cloud has been clearly detected. This leaves only two possibilities. Either an unknown natural mechanism produces acceleration without proportional mass loss, or some form of propulsion is generating thrust without expelling large amounts of matter. Avi Lowe has voiced frustration over the fact that the best high-resolution images, particularly those from the HiRISE camera aboard the Mars Reconnaissance Orbiter, taken on October 23, 2025, have not yet been publicly released. These images could provide resolution on the order of 30 meters per pixel, a major leap over ground-based or even Hubble data. Lowe argues that formal scientific requests and even letters from officials have not yielded timely results, while public-facing responses to prominent figures happen much faster, suggesting a double standard. He stresses that this data is time-sensitive and could have enabled coordinated global observations in the critical weeks following the detection. Delays, he says, are hindering the rapid scientific response the situation requires. Lowe has also proposed using existing assets, notably NASA's Juno spacecraft, when Atlas passes near Jupiter around March 16, 2026, at a distance of roughly 53 million kilometers. He suggests that Juno's dipole antenna could scan low frequencies, from about 50 Hz to 40 nanometer, to search for potential radio emissions undetectable from Earth. In addition, Lowe urges radio networks to continue monitoring, noting that Atlas's incoming direction lies within 9 degrees of the famous WOW signal detected in 1977. Detecting coherent radio emissions would strongly suggest artificial activity, though, as Lowe carefully notes, no such evidence currently exists. He calls only for coordinated continuous observation. Here's what has been confirmed so far. First radio detection, specific frequency lines recorded in late October, with well-measured Doppler shifts confirmed by MeerKAT. Jet network. Optical imaging reveals at least 7 jets and a 500,000 kilometer halo, including several starward jets, highly unusual for a comet. Non-gravitational acceleration. Orbital models require additional acceleration terms beyond gravity, like SNE, mass loss inconsistency. To explain the acceleration via outgassing, Atlas would need to lose charge of 1/16 of its total mass, 115%, starting from 5 billion tons, yet no massive cloud has been observed. Unusual photometric behavior, rapid brightening and blue shift near perihelion, distinct from standard comet behavior. WISE, pending high-resolution data. Early October. High-rise images remain unreleased, though critical for analysis. Origin trajectory. Atlas arrived from within 9 degree of the direction of the 1977 WOW signal. Juno opportunity. Predicted flyby near Jupiter. 53 million toler kilometers in March 2026. A unique chance for radio monitoring. Coordinated global tracking. Over 200 observatories are already following Atlas, with hundreds more expected to join after conjunction. Lowe concludes cautiously, there is no proof of technology, only a growing body of verifiable observational evidence. Hydroxal O radio absorption, a structured jet network, and measurable non-gravitational acceleration, alongside critical data gaps such as unreleased high-resolution imagery. He calls for transparency, rapid data sharing, and coordinated international monitoring, especially radio and optical, trying to track how acceleration evolves with solar heating. If large-scale mass loss is confirmed, Atlas would rank among the most active comets ever observed. But if no such debris cloud appears, we'll be left with a troubling question. What force is driving the acceleration without the expected loss of mass?